Okay, so let's start anyway with this session. My name is Alberto Rodriguez. I am associate professor at University Miguel Hernández in Elche, in Spain. We are going to start now session 9A about telecommunications engineering. We have 5 presenters on the paper, but only 4 so far have make presence here. So we will anyhow start with the same time, 15 minutes each, just in case in the last minute Professor Nikola Vucic appears. So any of you will have 15 minutes for the presentation and 3 minutes for discussion or questions. Please adhere to this time schedule because we would like to give time to everybody. And at the end, if we have time remaining, we can start discussing, okay? So we are going to start with the presentation called C-state characterization using experimental synthetic aperture radar raw data in 2 dimensions and the modified fractal signature method. Presenter is Professor Panayiotis Frangos from Greece.
Yes.
Panayiotis, you know you have 15 minutes.
Yes.
Okay.
Thank you very much, Alberto. So thank you so much. So I'm going now to share the screen. Here's my PowerPoint.
Okay.
Just 1 second, Alberto.
Yeah.
I cannot see the share screen. Just 1 second. Yeah. Okay. This is share screen. Yes. Share screen. Okay. So.
Yes.
Okay. Very good. And
there it is.
You can see it, Alberto. You can see it.
Yeah.
Very good. Thank you so much.
Welcome.
Yes. Just 1 second. Yes. So do it full screen. You can see it, Alberto. You can see it. Yeah. Thank you very much. So good afternoon, ladies and gentlemen. My name is Panayiotis Frangos, and I'm a faculty member, a professor at the National Technical University of Athens, Greece, School of Electrical and Computer Engineering. And this is a research work performed recently with some PhD collaborators of myself, namely with Mr. Kotopoulis, Mr. Massinas, who is just yes, he's just close to me, Mr. Massinas and Mr. Pouraimis, who are PhD collaborators. So the title of this research is C-state characterization using experimental synthetic aperture radar raw data in 2 dimensions and the modified fractal signature or MFS method. So some introductory material. The data for this paper were provided to us in a framework of a European working group in radar. These are real experimental data from the Norwegian Institute of Defense, Norwegian Institute of Defense, which is called FFI near Oslo, the capital of Norway. And this measurement campaign occurred in south of Italy in 2 days, 23 and 20, as you can see on this slide, 23 and 27 of September 2014, and these are called the NEMO trials. This international measurement campaign using synthetic aperture radar. And you can see the geometry on the left with the helicopter moving in vertical movement from downstairs to upstairs or the opposite. In 2 subsequent days, in the first day, 23 of September 2014, we had a rather high wind speed. So we have a turbulent sea, while the second day, 24 of September, we had the calm sea because of lack of winds. And the radar is a well-known picosar radar, which is a small synthetic aperture radar at X-band. X-band is around 10 gigahertz. Picosar, you know, is well-known in the industry, small radar. Everybody can buy that. You can visit their website to buy if you want a picosar radar, which is a small weight radar, which is now on board in the helicopter. The picosar waveform was linear frequency modulation, LFM, which is well-known, usual to synthetic aperture radar. Linear FM, linear frequency modulation. A pulse radar, of course, pulse radar, and the pulse repetition frequency PRF is 1 kilohertz. The radar sends 1,000 pulses per second, and the average range from the helicopter to the surface of the sea is about 1.85 kilometers. So this experiment was made for sea clutter analysis by using radar. Just 1 second, yes. Can close the door, Vasilis. Thank you, Basil. Yes. So the purpose of this study, of this experiment, was to make by radar sea clutter analysis by radar. And on the figure on the left, you can see that as the helicopter moves vertically, we collect the data. The data which were provided to us were N range profiles, N capital range profile. A range profile is the time response of radar signal, the time response. We were provided by about 50,000 range profiles, which we call raw radar data. And each range profile, which is the time response of the signal, is divided to M range bins. You know, in this study, M was about 574, I think, range bins for one range profile. Sometimes we call the time for one signal response, we call this fast time, while as the time for the range profiles in the other direction, we call this slow time in SAR terminology. The fast time and the slow time, which are actually the 2 dimensions of our signals. Actually, you will see that we will have now a 3-dimensional study of signals. So once again, in this transparency, you can see the helicopter moving downstairs or upstairs, and you can see the corresponding grazing angle, theta g, which is the grazing angle or the angle of the propagation of the waves with respect to the horizontal sea. This is called in radar terminology, is called the grazing angle. Once again, you can see in this transparency that the first day, 23 of September, we have rather strong winds, sea state 4 to 5. Grazing angles were from 3 degrees to 55 degrees, as you can see in the figure on the left. While the second day, 24th of September, we have very low speeds, wind speeds, and sea state 1. So turbulent sea and calm sea in the second day. Now here you can see some representative from the raw data that we have in our files from the Norwegians. We can see representative range profiles. On the left, we can see representative range profile from day 1, turbulent sea, and on the right, you can see from day 2, calm sea. And in general, the amplitude of the signals are higher for turbulent sea. These dependencies are rather well known in the literature. That is, for turbulent sea, you have a stronger signal back to the radar. Also, this, of course, this is dependent on the grazing angle, of course. Okay. And here on the horizontal axis, you can see that the fast time, on the horizontal axis, we have fast time. This is one range profile on the left. We have fast time, m equals 574 range beams in the fast time. On the right, the signal is, you can see that the signal is weaker. We have maximum up to 4,000 instead of 18,000 on the left. Now, my students did some interesting work on pre-processing these raw radar signals, which are real life radar signals. So first, there are three pre-processing stages. Stage one is averaging of the signals. This is rather well known in the radar literature. We call this incoherent integration of the signals. Incoherent integration means without phase corrections. And here, my students found that the number n equals 350 range profiles were appropriate for maximum SNR. Maximum SNR improvement. And also this to data reduction. So you can see here on the left, always on the left, you have the 3D signals on the first day, turbulent C. On the right, always we have the day 2 calm C. From here, you can see that on the right, you have more uniform, let's say, the distribution of the signals. You can see that. This is reasonable. And also you can see some outliers. And so in second stage, we have filtering of the signals to repress the outliers. As explained here, the outliers are some signal values which are erroneous or extreme, who are not justified by the majority of the signal values. And by some statistical techniques, these are depressed. These components are depressed. And my students used a method called box plot IQR statistical method for removing the outliers. This is well known in the literature. And so after removing the outliers, you have the 3D signals in terms of fast time and slow time for the turbulent C on the left and for the calm C on the right. Again, you can even here see that on the light we have some more uniformity of the signals, sometimes which is reasonable after all. And finally, we have the normalization of the signals. Here on the bottom of the page, you can see that we normalize the signals from 0 to 254 because we wanted to have these values as input to PNG images, as my students explained to me. So we wanted it to be normalized from 0 to 254, as you can see on the bottom. So after normalization of the signals, we have this kind of figures. So these are the raw radar data. No SAR processing. These are raw radar data, no images, not images. This is raw data as output of the radar receiver. Okay. After this, we have the classification method, which is a fractal method, which is so the output from this pre-processed data are input to the classification method, which is a fractal method called the modified fractal signature method. I'm afraid I don't have enough time to explain this. I will be very roughly. So once you have on the figure on the right, once you have the raw data, which is the middle 3D curve, you calculate the upper blanket, as you can see, and the lower blanket, and I'm sorry. Ultimately, by finding the volume between the upper blanket and the lower blanket, you find the area actually, the area A capital of the 2D surface, the area of that. And from the formula on the bottom, you find the fractal dimension of this surface. The fractal dimension is a function of iteration of resolution. I'm afraid I don't have time to explain this in detail. So after applying this fractal method, we found some very nice, usefully interesting results. Namely, you can see the green curves on the top, which are very well distinguished from the blue curves on the bottom. The green curves are for the turbulent sea, much larger fractal dimension, and the blue curves are for the calm sea. This curve is called modified fractal signature curve, modified MFS curve. And the mean value of this is the fractal dimension. You can see also the mean value of those curves, which are the fractal dimension, let's say. Once again, for example, the upper green curve is the MFS curve, the fractal dimension as a function of resolution or iteration delta. Here, keep in mind that the amplitude of the signals were kept from day to day. So this information of amplitude information was kept. And we had this promising results.
Have 2 minutes.
Thank you, Mr. Alberto. So I'm almost finishing. We give these curves also in another format. We can see the mean fractal dimension as a function of grazing angle, because in the previous figure, these curves were as a function of the grazing angle, of course, grazing angle. So in another format, we have these curves. While the green curve is for the turbulent sea and the blue curve is for the calm sea. And you have the pink lines, while the 95% lines of the measurements. Fractal dimension, mean fractal dimension as a function of grazing angle, well-distinguished curves. So finishing with that, we summarize here our method, the preprocessing sim and the discrimination sim with fractals. And here we show possible future research. For example, the first point here is that we can do this for fully operately from commercial point of view. We can progress to a fully commercial software tool to estimate the mean height of the surface waves. Keep in mind that the amplitude information is important from day to day. So we need some kind of calibration before this becomes fully commercial. Calibrating the data and so on. And also we intend to make further simulations by using well-known simulation tools, because this was based in experimental results, and possibly use also other fractal methods. This is thanks to the Norwegian Institute for Defense, which provide us this data in a framework of international working group on radars. And here is the bibliography. So, Alberto, I think this is the point, more or less, the key points, if I am correct.
Okay, thank you very much, Professor Frangos. Thank you very much for your presentation, very nice. Is there any question from the audience? Any question from the attendants on the internet? Okay, we'll have just a very fast one. Yeah. Please be brief. It's just in the last figure you show.
Yes.
This one. From here, it is, from my point of view, it is clear that it doesn't matter actually the grazing angle. So you can estimate the state of the sea regardless of the grazing angle, more or less, because the difference is very high between the two fractal dimensions.
Yes.
So that's make it very, not easy, but I mean very reliable. It is very reliable system.
Yes.
Good.
Yes.
Okay.
The answer is yes. But just keep in mind, Alberto, that the first day, the green line was a day with rather strong wind speed.
Yeah, I see.
So in real life, when you have your helicopter or aircraft, you want to make real time from the radar on aircraft. Real life, you want to estimate for example, the height, the mean height of the, and you will not have so ideal situation, of course.
So these are extreme conditions.
Extreme conditions, yes. Extreme conditions.
Okay,
yes.
But anyhow, it is really interesting. Thank you very much.
And perhaps finish, Alberto. Last year you presented. This is better. Last year, one very small comment. Last year you presented two-dimensional analysis. But I think we think this is better because this is a full information is there is a 3D set of signals, and also this is very fast in computation. All the computation time is 1 second or 1 second. This is very fast. It's better than the previous year's results.
Okay. Thank you very much, Mr. Frangos. Thank you very much.
Thank you, You're welcome. Thank you very much.
Please, could you just stop sharing your presentation?
Yes. Thank you so much.
And we have here Nikola Vucic. Yes, there you are.
Yes, I'm here.
Okay, thank you very much, Nikola. So you have 15 minutes, okay, for your presentation. The presentation, Professor Nikola Vucic is evaluating similarity of spectrogram-like images from DC motor sounds by Pearson correlation coefficient. You have 15 minutes, please.
Yes, thank you.
Sure you get to that timing, okay?
Yes, thank you. My name is Nikola Vucic. I'm teaching assistant of the Faculty of Electronic Engineering from the University of Niš, Serbia, and I'm going to present you this paper. So this is the short overview of my presentation. So to introduce you shortly, the topic of this paper is similarity of spectrogram-like images obtained from direct current motor sounds. In that respect, relevant measures of image similarity are first reviewed, and then one of them, the Pearson correlation coefficient, is applied for evaluating the similarity within the same class and between two classes of different spectrogram-like images. So we are assessing similarity of images in an objective way, contrary to the subjective way like the usual with the human eye. So shortly to introduce you to the image similarity measures. So we suppose that we have two non-negative images X and Y of the same size as you can see here, whose similarity should be assessed and represented as X and Y, where we have this parameter I as the sample index, and N is a total number of image samples or the pixels. So we compare two types of image similarity measures. First is Euclidean distance, and the second is Pearson correlation coefficient. So the first one is Euclidean distance, and it's a distance-based measure. As you know, in geometry, you just calculate the distance, and it's more simple, and it's used mainly when the data to be compared are continuous in nature. But we focus in our paper on another measure. It is a Pearson correlation coefficient, and it belongs to the similarity-based measure. So I will explain you what is this Pearson correlation coefficient, or PCC. So the Carl Pearson defined it in 1895 as the Pearson product moment correlation coefficient, the first formal correlation measure that provides the degree of correlation between two quantities like images. So the calculation of this coefficient for monochrome digital images rho, which is also often denoted by R, is given with this formula. It's rho with the indexes X and Y. It's sigma XY divided by sigma X and sigma Y. So this sigma XY is the covariance between X and Y, calculated as defined in the theory. So, and we have the expectation E from the samples X and Y, and these are sigma X and sigma Y are standard deviations of these signals. So it should be noted that the covariance sigma XY is always smaller than the product of the standard deviations sigma X and sigma Y. So the PCC can also be represented in the following way. You have the explanation down in the comments, so I will proceed with the next slide. So it's important to say that PCC has values in the range from -1 to +1, whereby the value 1 indicates that the two compared imagers images are absolutely identical. 0 indicates that they are completely uncorrelated, and the -1 value shows that the images are completely anti-correlated. So some of the main benefits of the PCC as a dimensionless indexer, it condenses the comparison of two-dimensional images down to a single scalar value R, and it is invariant to linear transformations of variables X and Y, which means that R is insensitive to uniform variations in brightness or contrast in an image. On the other hand, limitations of the PCC are that computational demands limiting its usefulness for image registration. Next is that its extreme sensitivity to the image skewing, puncturing, and wedge netting that inevitably occur in imaging systems. And the third limitation is undefined calculation due to the division by 0 if one of the test images has constant uniform intensity. So that's the theoretical approach to this paper. And now I will explain what have we done here. So we have the audio signals of direct currency motors that are classified in two classes. So first is OK motors, the motors without failure or malfunction of type A and direction of rotation 1, they belong to the class 1, and not OK motors with certain failures or malfunctions of type A and the same direction of rotation 1 belong to class 2. So the class number 1 contains 281 signals, while the class 2 contains 387 signals. So the audio signals of DC motors are used for calculating various spectrogram-like images. We have focused on these 7 spectrogram-like images, as you see here. So first, the audio signals are pre-processed by extracting 5 seconds of usual signals. So these samples are longer, like 15-20 seconds, and we use the 5 seconds that are the best ones. So each audio signal is then transformed into defined spectrogram-like images, applying the mapping relevant for every particular image with the aim of exploiting the maturity of the image technology. Thus, the STFT yielding complex values as a result are used for some of the images. So the F component of the discrete Fourier transform of the teeth frame of signal X is calculated, as you can see here, whereby W is a window function. So a spectrogram is generated from STFT results, and it's given as a matrix, where each column is the DFT result of a particular signal frame. So further, the obtained images in the form of matrices are converted into arrays by concatenating the columns. So from matrices, we got the arrays. So these arrays representing numerical parameters of the concrete audio signal are used for the analysis of similarity among the spectrogram-like images within the same class, that's intraclass, and between the classes 1 and 2, that's interclass. So this is done by calculating the PCC for each combination or pair of a particular image, its array, and all other images of the same type belonging to the same class, and all other images belonging to another class. So the numerical results obtained for the PCC are processed to extract the following statistical quantities: mean, minimum, maximum, median, and standard deviation. So this is the table with these statistical parameters for intraclass comparison within the class 1. For OK motors, these are the PCCs for not OK motors intraclass comparison within class number 2. We see the different statistical parameters, and this is the interclass comparison between OK and not OK motors. So we have also made heat maps for these PCCs. So in first 2 columns, you see intraclass comparison. First is for OK motors, second is for not OK motors, and the third column is for interclass comparison. So as you can see, first 2 columns have the squaric shape, and this white line it's the main diagonal, it's the Pearson coefficient equal to 1 because it's compared with itself. And all the heat maps in columns 1 and 2, they're symmetrical according to the main diagonal. So we have first 3 spectrogram-like images in these 3 rows, and the next 4 are here. So we got some nice heat maps. And then we try to order samples based on image similarity. So the previously presented results show that the difference of the PCC values among the sound samples within the same class, even within the class 1, is rather large in most of the applied spectrogram-like images. So the PCC values for the lean power spectrogram within the class 1 ranges from 0.17 to 1. So as you could see in the table and the heat map, this situation is analyzed now in more detail using only class 1 and lean power spectrograms. So first, the average PCC for each DC motor of class 1 is calculated across all motors of that class. So then the motors are then rearranged according to the average PCC value in a decreasing order. It's the next slide image. And the largest average PCC is about 0.73, while the smallest is about 0.36. Although the PCC value decreases rather continuously, the PCC curve can be split in 2 parts up to the 200-second motor, denoted by the vertical line in the next slide's image and above that motor number. So these 2 parts have different slopes, where the slope of the first part is smaller than that of the second part. So you have see the decreasing curve, and the green line is already explained. So we have PCCs for OK motor L with the largest average PCC, and S with the smallest average PCC within class 1, and the image A is before rearranging and image B is after rearranging. So you can see and this green line. So the limit marked as green line divides class 1 into 2 subclasses 1,1 and 1,2, where the first one contains the motor with larger correlation coefficients, and the heat map of the PCC values for the rearranged motor is shown on the next slide. The motor with the largest average correlation is located in the upper left corner, and the correlation decreases going further away from this corner, which is denoted by a darker color. So the introduced limit between 2 subclasses is denoted here by both horizontal and vertical lines. So you can see this heat map here. You have subclass 1.1 here, and this is subclass 1.2. These 2 squares are intra-class comparisons, and this is inter-class comparison between subclasses 1 and 2. And this heat map is also symmetrical according to the main diagonal. So we have shown also the lean power spectrograms for motors L and S. So you can see their spectrograms are quite different. And these are the PCC values for these statistical units as previously shown. So subclass 1, subclass 2, and between these subclasses. So to conclude this paper, based on the results obtained related to the evaluation of the image similarity, the applied spectrogram-like images can be divided into 2 groups. So the first includes the lean power spectrogram, MEL spectrogram, gamma tonogram, and CQT power spectrogram. And the second group, it includes STFT and CQT chromograms and tempograms. So the images from the first group give larger PCC values between the OK motors, intra-class similarity for class 1, and smaller PCC between the not OK motors, intra-class similarity for class 2, as well as between OK and not OK motors, that's inter-class similarity. So this is not the case for the images from the second group, where it is hard to see a significant distance between the intra-class and inter-class similarity. Therefore, the images from the first group are considered here as a better option for using them as input to a deep learning model. So, and among the images from the first group, The lean power spectrogram represents an image with full resolution on the y-axis, meaning that the size of an image is significantly larger than in the other three images from this group. So consequently, the preference for usage as a deep learning model is given to the other three images of the first group. When they are compared, the greatest relative distance between the intraclass and interclass similarity is obtained for the MEL spectrogram. So thank you for the attention. You can see that this paper and research were supported by the Ministry of Education of Serbia and the Serbian Science Fund. So thank you once more for your attention. If you have some questions, I would be glad to answer you.
Thank you very much, Nikola. Thank you very much for a very nice presentation. Is there any question from the audience? If not, yes?
But Alberto, I can ask a short remark. Yes. Yeah. This is Panayiotis Frangos from Athens again. Thank you for this nice presentation. I just one short remark, please. Listening to your presentation and talking about audio signals, analysis of audio signals here from motors. I just remembered that some friends of mine from Bulgaria are working on signal analysis from church bells. So they had some project in Sofia, in Bulgaria, for analyzing the audio signals of the church bells. So possibly your research may be also applicable to other applications. I mean, this is my point. Thank you.
Professor Frangos, thank you very much. Sofia is quite close, just 150 kilometers. So if you
yes.
can send the contact these Bulgarian colleagues, we would be very grateful.
Yes, very nice idea. Very nice idea. Because friend,
thank you.
Yeah, thank you. Yes, I will do that. Yes, this is a very nice idea. Thank you so much.
Thank you.
I will do that. Thank you. Thank you.
Okay, thank you, Professor Frangos. Any other question from the audience? I think there is something. Okay.
Yes, Ritonia from University of Maribor. My question is about the failures. Which failures were made by the machines in commutator or brush system?
Excuse me?
You talked that in second class was the machines with failures. What kind of failures? Yes, in commutator, in brush system? Or?
Those are electromotors, so they're pre-labeled. We got the samples already labeled as okay or not okay. So we don't know what are the failures exactly. Some not appropriate sounds in rotations and so on.
Okay. And do you have any perhaps tests also with other kind of machines, induction, synchronous? No.
No. For this research, we got just the electromotors rotating. We got two directions, two classes of okay or not okay, different types of motors. So in this paper, we focus just on this to make two subclasses within one okay motor class.
This was the order from your factory. You have a factory about this on your, and you work for test these machines.
No, we got the samples. We didn't record the samples.
Okay, thank you for answers.
Thank you very much.
Okay, thank you very much. Any other question? Okay. If not, then we will go to the next presentation. The next presentation is called A Novel Approach for Polyphase Filter Bank Design Using ABC Algorithm. The presenter is Ahmet Logoglu from Turkey. Please, Ahmet, you have 15 minutes. You can start. Once you start, you can share your presentation.
I see. Thank you. Can you see my presentation?
Yes.
Hello everyone, good afternoon. My name is Ahmet. I am working at University of Osmaniye Korkut in Turkey as a lecturer. A novel approach for polyphase filter bank design using ABC algorithm. This research was supported by the Georgios University Scientific Research Project Center. Polyphase filters play an important role in the design of various filter structures as they reduce the complexity and therefore the cost of the filter by decimating before filtering, reducing the number of multipliers for samples in the filter inputs. As we will show in this study, filters of this structure are full-pass filters with different phase shifts, so we call these structures polyphase filters. The structure shown in equation 1 shows n-channel polyphase decomposition, and these are the polyphase components. Figure B shows that block diagram for the polyphase filter structure, delay, process, and output. It is got by sample reduction of the delayed phase-shifted form of the original impulse response. It's obtained by taking the Z transform of the output sequence to get an M-channel polyphase filter structure. There are two major benefits of using a polyphase filter. The first is to reduce the resource usage, and the second is to reduce computational complexity. In this paper, a novel polyphase filter bank design approach was suggested using ABC algorithm to optimize filter coefficients. To demonstrate design performance, a reconstruction application of polyphase filter bank was realized according to a shield resourced by ABC algorithm. The motivations and contributions of this paper are given as follows. To the best of our knowledge, there is no study describing polyphase filter bank design based on meta-heuristic algorithms in literature. Varying filter lengths and frequencies are analyzed. The performance of ABC algorithm was compared with those of the well-known heuristic algorithms, example, genetic algorithms, particle swarm algorithms, etc. The improvement effects of control parameters on the solution performance of ABC algorithm was investigated in detail. A reconstruction application was realized for the suitability and feasibility of the design approach. Optimization algorithms. We use artificial decolonal algorithms. Proposed model in the study, a novel polyphase filter bank design approach was suggested using ABC algorithm to optimize filter coefficients. Especially ABC algorithm was effectively used in the prototype FIR filter design. Besides ABC algorithm, PCO algorithm and genetic algorithm are used in the design of the polyphase filter bank. The proposed model approach is briefly shown in Figure 2. Figure 2 shows that the schema of the proposed model, prototype filter design with algorithms, polyphase filter design, sinusoidal signal application. First of all, a specially designed frequency response is used for the full filter design. The frequency response of the filter coefficients optimized using the optimization algorithms is aimed to obtain the desired and predefined frequency response. In this study, the effects of the control parameter change of the artificial decolon algorithm on performing the polyphase filter bank design were investigated. Determining the control parameters of the algorithm is one of the most important factors that directly affects the working performance of heuristic algorithms. In the first study investigated of control parameters of the algorithm, filter length was taken as 32 in the polyphase filter design problem by giving different values of control parameters such as population size, limit value, and maximum number of cycles. The algorithm was run 50 times and the lowest mean square error values are obtained. The parameters and change values of the ABC, PCO, and genetic algorithms are shown in table B. Table will show that parameter values of ABC, PCO, and genetic algorithms, meta-heuristic algorithm, and control parameter values. ABC algorithm, population size 10, limit equal 320, maximum number of iteration 1,200. The parameter analysis study for the ABC algorithm is shown in table 3. In cases where the population number is 10, better results were obtained in the population number search in the algorithm. Figure 4, convergence curves for the filter length value 32 of the ABC, PCO, and genetic algorithms. In figure 5, the graphs of the filter input and output signals in the polyphase filter bank design realized with the ABC algorithm are given for filter lengths 8. As can be seen from the graphs, the overlap of the input and output signals is quite right in case it shows the success of the design filter. In the next study, algorithm performance for polyphase filter bank output will be examined in terms of reconstruction error and spectrogram. Filter bank design will be tested with different filter lengths and algorithm parameters to be compared, and the results will be evaluated. It's foreseen that the designed polyphase filter can be developed thanks to future studies. Conclusions in this paper, polyphase filter bank was carried out for the first time with ABC algorithm. In addition to this, a novel approach for polyphase filter bank design using ABC algorithm was suggested, and the best of our knowledge, there is no study describing polyphase filter bank design based on meta-heuristic algorithms in the literature. The varying filter length and frequency are studied in detail. The results obtained were compared with the results got with well-known optimization algorithms such as PCO and GA. As can be seen from the result, a successful and effective design has been realized with the ABC algorithm. In this paper, the best result obtained in the range of WS 0.4, 0.6 in the study of the stop band and passband frequency range used in the prototype filter design performed with the ABC algorithm. In our future studies, the analysis of the design filter bank will be carried out in real-time systems. Thank you for your attention.
Okay, thank you very much, Professor Logoglu. It was very interesting. Thank you for the timing. It was very good. Is there any question from the audience, from any of the presenters, or anybody from the internet, or in the room in Palanga? Okay, I just have a brief question, because I was not sure. In the graphic in which you show the convergence of the methods, that one, it looks like genetic algorithm and ABC are more or less the same. Okay, but PCO is faster, I guess, no?
Yes.
A bit faster.
Fast.
Then you say that the results were good for the ABC, but I mean, is in any way ABC better than PCO, or it is just something you are not sure, you're still trying to develop? I mean, why would you use one algorithm better than the other one? Is there any specific advantage, or only you know what I mean?
ABC algorithm taken our studies because ABC algorithm faster the PCO, faster than PCO, and 1 minute, please.
Yeah.
ABC algorithm faster and stable.
Okay. Okay, thank you very much. This is it. Any other question?
Alberto, if you permit me, perhaps I missed the point. Possible applications of this research, in which areas possible applications of this research? Perhaps I missed the point. I'm asked to the author, what are possible applications of this research?
Sorry, I didn't.
Which applications can this be used for? But I think that, I mean, this is a general purpose. The idea of this is to improve the design of the filter in ways of make it faster or more accurate or reliable. So, but once you have designed a proper filter, it can be applied to anything, I guess.
I understand. Yeah, I understand. Thank you. Thank you.
The aim of this study, the filter response, real-time ideal filter.
Okay.
Real-time close to the ideal filter by using meta-heuristic algorithms.
Okay. Yeah. So it is. Once you improve the filter performance, it can be used for anything. So it is very practical if you do it. So thank you very much for everybody, and then we will go to.
Alberto, we can hear you.
Yeah. Sorry. I saw that. So we're going to the next one, to the next presentation by Professor Sili Baxi from India, with the work A Novel Meta-Heuristic Optimization for Through-Output Maximization in Energy Harvesting Cognitive Radio Network. So please, Michele, when you want, you can share your slides and start the presentation.
Good evening. Is it visible to everyone?
Yeah, thank you.
So I'm Shelly Bakshi from Thapar Institute of Engineering and Technology. Today I'm going to present the paper based on the topic, A Novel Meta-Heuristic Optimization for Throughput Maximization in Energy Harvesting Cognitive Radio Network. So the key points for this paper are: a novel meta-heuristic optimization algorithm has been proposed in this work, and the novelty of this proposed algorithm is tested against the various benchmark functions, and then to check the validity and the effectiveness of the algorithm, the already existing state-of-art algorithms are compared with this meta-heuristic algorithm. So performance comparison of the algorithms is also made. And then this novel algorithm is applied to the energy harvesting cognitive radio, wherein we have taken the problem of throughput maximization. So These meta-heuristic techniques, these are very new techniques, and these are used for optimization purposes in wireless communications these days. I'm getting a request of remote control. Should I approve it or decline?
I guess you should decline it.
Okay.
Maybe you can maximize the presentation.
Yeah, is it visible now, sir?
It is visible, but maybe if
Okay.
you maximize it, it will be easier or better. But anyway, it's up to you.
Somehow I can't see the presentation, the slides.
You can or you cannot?
Cannot.
You cannot.
Mm-hmm.
Okay, I can see them. Is anybody else not seeing them? Because I can see the presentation.
Is it visible, Serdar?
Some of us.
Maybe you could stop and start again the sharing of your slides.
Yes, please. Yeah.
Okay, okay. I will do that. Okay, I have done. So these
Hold a second. Now this is it.
Yes,
Everybody
perfect.
Okay, perfect. Thank you very much, Miss Basil. You can keep going, please.
So these meta-heuristic optimization techniques are the modern optimization techniques. The main important point in meta-heuristic techniques is they use the intensification and diversification. That means these meta-heuristic techniques, these algorithms, not only search for the local search area, but they have the global, that is the global search is also there. So that makes these techniques very well to be used for any application. So in the broader category, they are based on evolutionary and swarm intelligence. They use the probabilistic approach. They require the different controlling parameters like population size, number of generations, and the convergence rate of these algorithms is faster because of their capability of exploration and exploitation. They converge faster than other algorithms, other traditional algorithms. So there is no particular algorithm is fixed for any kind of a problem. We can use different algorithms for solving different problems depending upon their convergence, depending upon their exploration and exploitation capability. So in this work, I have used the basis for multi-objective antline optimization. This is a multi-objective wherein two or more conflicting objectives are considered, plus the problem which is having the constraints also. Suppose in our work, there are constraints on energy and sensing time. So the constraints are also considered, and the multi-objective problem has been formulated in this work. So multi-objective optimization antline algorithm, this has basically having the two mechanisms considering simultaneously. One is the population set of the ants, and other one is the population set of antlines. So there are basically 5 steps that are used by the multi-objective antline optimization. It mimics the hunting mechanism of the ants and antlines. So whatever optimal solution we are going to find for the problem, this optimal solution for the optimization problem is approximated by employing a set of random solutions. So the random solutions are generated, and out of those random solutions, the optimal one is found. So these solutions are improved based upon the principles inspired by the ants and the antlines. So the principles involved in this mallow are the random walk of the search agents, wherein the ants, the population of the ants are initialized with the random values, and the fitness value of each ant is calculated in different iterations. Once the ants move towards the ant lines, that is the trapping of the ants is done, then sliding of the ants towards the ant lines and catching of the ants, and then again the reconstruction of the pits in which the ants are captured is done. And the final step in this mallow is the elitism. In elitism, what is happening there? That there are different ant lines, and out of those ant lines, the elite ant line is selected upon depending upon each iteration. So the elite ant line is the, if we compare it with the other problem, the elite ant line is the optimal solution of the problem. So now this mallow is the already existing algorithm. It works upon the selection mechanism of the roulette wheel. So in order to enhance this mallow algorithm, what we have done in our work, we have improved the mallow algorithm by using the rank selection mechanism, wherein all the solutions are stored in the repository, and out of all those solutions, they use the roulette wheel mechanism, and the solutions converge based upon those mechanisms. But when we are having a problem, especially in the domain of wireless communications, when we are having wireless sensor nodes, cognitive radios, there are very minute differences between those cells. There is that means the time required, whether it is sensing time, whether it is throughput, we require very optimized value. So there are very near values. In case of those near values, this mallow does not work effectively. So what we have done in the work, we have used the rank selection mechanism, incorporated the rank selection mechanism in our work. So depending upon the rank selection mechanism, the mathematical model for the rank-based multi-objective ant line optimization that we have used in our work is the fifth step, that is the updated position of the ants. This position of the ants is updated based upon the rank selection mechanism. We are having the step number first, that is the random walk of the search agents, wherein the ants are initialized with random variables, and this xt is the random walk of search agents, and we have the cumulative sum of all these depending upon different number of iteration. We have taken n number of iterations, and trapping of ants, then sliding of the ant towards the ant lines, and finally catching of the ant line. This catching of the ant line, this ant line is the jth ant line at tth iteration, which gives us the final position of the ant line. And now when we get the different set of ant lines, out of those set of ant lines...
Sorry, wait a minute, Mr. Baxi. They say that maybe your PowerPoint is frozen because we are not sure if you are passing the slides or not. I guess.
Is it visible now?
Yes, but can you change the slide just to see if it works?
Yeah, I can change the slide. I have changed the slide, sir.
No, I'm afraid it's not working.
No, not working.
No.
I think the solution could be if the presenter will switch the camera off. Maybe it is related to the internet.
Okay, we can try this.
Is it visible?
No, well, it is visible, but please, can you again
I will just share again.
Yes.
I will share again. Sorry for the inconvenience.
No problem. Then you switch the camera off, and then we try again. Okay, there we go.
Oh, okay.
Yes, yes, okay, thank you.
Is it visible, sir?
Yes, yes.
Okay. So this updated position of ants, once this updated position of ants is based upon the rank mechanism, we find the different ant lines, different solutions of the optimization problem. Now, to see the competence of this Romolo algorithm, we compared this Romolo algorithm with the already existing state of art algorithms, multi-objective optimization algorithms like multi-objective particle swarm optimization, multi-objective moth flame optimization, multi-objective ant line optimization, And we tested these against different test functions. And as per the different test functions, we can see this R-molo is, we have plotted the convergence characteristics of these test functions against each algorithm. So we can see that R-molo, that is rank-based multi-objective ant-line optimization, it outperforms the other algorithms for the functions ZDT1 and Oakley and Dejan functions. So we can see that the convergence of this is faster as compared with the already existing multi-objective algorithms. Now this algorithm is applied to the energy harvesting cognitive radio, wherein we are considering an energy harvesting cognitive radio in which there is a set of primary transmitter receiver pair and a secondary transmitter receiver pair. The secondary transmitter is harvesting the RF energy from the primary transmitter using an RF energy harvester. And the problem here is that this primary transmitter and primary receiver, they are using the licensed frequency band, whereas the secondary transmitter and secondary receiver, they are not licensed to use the spectrum. So they will be using the licensed spectrum when the primary network is not using that spectrum. I mean, when the primary receiver is not using the spectrum, at that time, the secondary transmitter is going to use the spectrum with the energy that is used for sensing and data transmission, that is the harvested energy from the RF signal of this primary transmitter. Now we have considered the frame structure for this separated energy harvesting and spectrum sensing scenario, wherein the harvesting and spectrum sensing are done at the different time slot. What the problem here is, we need to improve the data transmission time and taking the constraints on energy and collision into consideration, because there is always a chance of collision and there is always a lack of energy. So we want to improve the throughput of this cognitive radio network. So for that, improving the throughput means we have to optimize the spectrum sensing time. That means the sensing done by the secondary transmitter or the cognitive radio, that is to be minimized. So the problem formulated is maximization of the throughput subject to the optimizing of the sensing duration, and also subject to the different constraints on the collision between the primary network and the secondary network, and to the constraints on the energy. That means whatever energy is consumed by the spectrum sensing or data transmission, that should always be less than the harvested energy. There should be sufficient energy, and that is stored in the battery. So these are the system parameters which we have taken for the simulation purposes. And this problem is solved using the different algorithms, and the comparison of the proposed R-molo is again compared with the different classical state-of-art algorithms. We can see that the mean fitness value of the throughput, we have taken different harvested energy values. These are the 3 different values for which we have designed the system, and we can see that the throughput is maximized for the maximum energy harvesting. Now, what we infer from these observations, that the proposed R-molo is converges faster. This proposed R-molo, it is having the mean high fitness value for the objective function which we have selected for the energy harvesting cognitive radio. And this is the statistical results for different harvesting energies. We can see that R-molo outperforms the other algorithms in comparison. And again, we have made a comparison with the state-of-art techniques, that is R-molo for signal to the noise ratio of -28 decibels is compared for the normalized sensing duration. And we can see that this is again having a higher throughput as compared to the already existing techniques. So the key observations from these are that the shorter the sensing duration, higher will be the average throughput. But as soon as the sensing duration increases, the throughput tends to decrease. We can see from these graphs that the throughput will tend to decrease as the sensing duration is increased. So, so this R-molo is having the higher throughput as compared to the other benchmark algorithms, and we are having the optimal value for the sensing duration. Now, the direction, future direction in conclusion from this is, we have compared this with the already existing heterogeneous and homogeneous network. And this meta-heuristic rank-based multi-objective ant-line is showing 14.2% improvement over the other two schemes. And this is also compared with a SNR of -15 dB with the population size of 20. And we have considered this for the 500 iterations, and the archive size is 100 taken for this. And the improvement is 16.33% is efficient. So this meta-heuristic technique ran this multi-objective art-line optimization algorithm is better than the other traditional algorithms. And if we consider the future direction of this work, since these meta-heuristic techniques, these are giving us the good results in cognitive radio. So these meta-heuristic techniques can be hybrid. There can be hybrid meta-heuristics also. We can hybrid it with the either the different meta-heuristic algorithms. That means we can combine the two meta-heuristic algorithms, the features of one algorithm with the other features of other algorithm, or rather we can also combine it with the machine learning techniques, meta-heuristics and ML in the future. And we can also use these, this has been used for the single directional networks. We can also use for the bidirectional networks in the near future. So this is the principal glossary that has been used. This is the flow chart of the RMOLO. And these are some of the references used for the work. Thank you.
Okay, thank you very much, Ms. Baxi, Professor Baxi. I think it's very interesting. Any question from the audience, from the internet or from the room? No? Okay, if not, I have just one thing which I am curious, just because, but I'm not sure about the possibility of what I am asking, if it is not a silly question. But you said that the shorter the sensing duration, the higher the throughput, no? It looks obvious, but have you checked which is the lower limit for this? I mean, for which it stops working? So can you reduce the sensing duration as much as you want, or is there a limit?
Yeah, basically, if we see from here, this sensing duration, this tau2, this is to be optimized. This is to be reduced so that we get enough time for the data transmission. Then only we can get the increased throughput. So this sensing duration, this is depending upon different algorithms. We have the different values for the sensing duration. It depends upon the algorithm which we are using.
Yeah, I see. But
and the problem under consideration, whatever problem we are taking, whatever frame structure, because here I'm using the separated harvesting and sensing. Harvesting is done in different slot and sensing is done in different slot. So I need to optimize this part much so that I can get higher throughput.
So the optimization process is aimed to minimize the sensing duration. Okay. Okay, thank you very much. Any other question? No? Okay, thank you. So we are going to go for the last presentation, evaluation of long-distance IEEE 802.11ah wireless technology in Linux using Docker containers. Presenter is Daniels Alexandrovs Moisic from Latvia. I don't know if the name is correct.
Yeah, Alexandrovs Moisic.
Letters, but
okay.
Okay. 15 minutes. Okay.
Yes, I know. Have you seen my presentation?
Yes, we can. Thank you.
Okay. Wait. One moment, please. Okay. Hello, everyone. Labdien visiem. My name is Daniels Alexandrovs Moisic. I'm from Riga Technical University, and I today want to present my article, which names Evaluation of Long Distance IEEE 802.11h wireless technology in Linux using Docker containers. I'm glad to present to this conference my article. Okay, let's start. Starting from abstract, my article, wireless technologies are essential for modern users to maintain uninterrupted connection to internet. Without internet, can establish a connection to internet using some wireless communication. The most popular wireless technology standards are standards of IEEE 802.11 family. Nowadays, data transmission rate to IEEE standard can reach up to 10 gigabits per second using a new standard Wi-Fi 6 or another name IEEE 802.11ax. Different IEEE standards have specific data transmission rates. For example, our expected standard is Wi-Fi Hello or IEEE 802.11ah. It operates an 900 megabits band, which works on an unlicensed frequency band below 1 gigahertz, and it's called sub 1 gigahertz range. The great benefits of Wi-Fi Hello standard is low energy consumption, which enables Internet of Things devices communication over long distance without using a lot of energy. Wi-Fi Hello standard is being studied by authors in discrete even network simulation program, which with Wi-Fi Hello model, what was installed and implemented in Docker containers and virtual machines, which running Linux operating system. During the simulation, results were obtained for Docker containers simulation with limited number of stations over different simulation times. These results have been studied in different scenarios. In the scenarios, results of Wi-Fi Hello network simulation were converted into another simulation time, and those were compared with each other. In our article was used some technology, for example, Linux Ubuntu operation system on virtual machine, what was installed on my host machine, host computer. Docker containerization program installed Daemon client server architecture and was added containers for experimental part. After this, on virtual machine with graphical user interface Linux operation system and on containers, absolutely was installed a discrete event network simulation with required model. What was needed for our experimental part for throughput Wi-Fi Hello analysis. Containers have different compared to the structure of the virtual machine. Containers were designed, distributed, and operated for products. Developers can build software locally and based on certain what it will work in the same way regardless of the host environment. Containers can be used and extended at a phenomenal speed throughout the industry. Docker is a platform as a service assembly product which uses operating system level virtualization to deliver software in packages. It's called the container. The containerization architecture is a client-server environment. On the client side, containers communicate with Docker daemons on the host. Daemon and containers can be installed on a single host machine and both can control it remotely. Daemon and containers communicate through the Docker Zero interface bridges on Linux operating system. And Docker architecture consists of three components: images, registers, and containers. Docker image is a read-only template used for deployment of Docker container. The image may contain, for example, an operating system, web server, mail server with additional pre-installed settings. I think what the main goals of this article are using discrete event network simulator in terminal version for education things, because in the one Docker virtual platform, you can run simultaneously a lot of containers with different simulations. For example, in one simulation, you can attach one type of IEEE environment of Wi-Fi Hello simulation. On the second simulation, on second container, you can run 30-second simulation time for throughput analysis for one modulation and coding scheme. The first scheme uses a host computer which installs hypervisor VirtualBox software. The virtual machine operating system is Linux with additional software installed and configured in the hypervisor. Discrete event network simulation with required Wi-Fi hello model, and connection was set up between a virtual machine and host computer via secure shell protocol. The second scheme is quite difficult, but at the same time also interesting as an application. The first scheme was complemented by Docker Daemon and containers with Linux operating system and required programs, which were used in the first step scenario. 3 more containers added with different IP addresses have added to the Docker Daemon. In these Docker containers, a user or developer can set up connection between containers themselves, as well between containers and Docker Daemon. This technology called Docker networking. Docker includes network container support via network drivers. In our case, all containers were connected to virtual bridges using the same principle as a normal network. More tool has been installed in containers to measure Wi-Fi hello parameters and measure throughput for every simulation time. Here we can see common results of throughput for virtual machine and containers. It will choose throughput for 264 and 256 stations for comparative picture, because it's possible to see how was changing throughput after manipulation with modulation and coding scheme changing. Looking at the common results of virtual machine can make an opinion what for 64 station and 256 station and 1 megahertz band, the best modulation is quadrature amplitude modulation 256, which coordinate rate 5/6. If compare result in one group, can make a conclusion what 64 stations better throughput than 256, because was spent less energy on the performance of stations, and also we can say what in 64 station results throughput result is better. At 2 megahertz, this station is same but different, was used different modulation coding scheme with different coding rate, 3/4. On Docker container is situation better. At the 1 and 2 megahertz band, we can look what the common results of Docker containers throughput and simulation time, can make a conclusion what result with the same parameters is better. Is indicate what Docker containers uses lost less energy and less computer performance on the simple host machine. At graphs, we can see what throughput results on 64 stations better than 256 stations. In real life, without simulation, what measurement was done in one restricted access window group. Can make an opinion what in one restricted access group better using from 32 station till 64 station for better results of throughput. If you are using a lot of station in one group, therefore didn't increase internet throughput result and peak energy consumption of stations. Definitely can have an opinion what if you want to make a simulation, the best simulation infrastructure is Docker containers, which take less performance of host machine. Docker containers didn't have additional installed programs and system resource. Yes, as a second graph, we can see what the Docker containers results is better than virtual machine. In the Docker containers, simulation are seen to be better than in virtual machine. If you use the device connection to all access point or Internet of Things devices to one main access point, then better use the environment of Docker container simulation. The results were found to be directly influenced by the number of stations and the dependency of the modulation coding scheme on the number of stations. At 64 stations, the throughput rate increased depending on the modulation coding scheme. Docker containers produce slightly better throughput rates than the virtual machine from 0.1 till 0.2 megabits per second range. In containers, it can be concluded that the simulation processes take place more quickly, both at the total simulation time and the encoding speed. The high number of stations may still operate at the rate of 5.2 megabits per second. The wider bandwidth of channel supply speedy data rate and elevated transmission quality. The capacity rate indicator can be only improved in a large group of stations and was made to look at the capacity of correlation result for speed depending on the total number of group and the number of stations in each group. This allows you to see how many groups can transmit data with maximum rate of the modulation and coding scheme. Thanks for attention. Paldies par uzmanību.
Okay, thank you very much, Daniel. It was a nice presentation. Is there any question from the audience? Any question from the internet? Any question from the room in Palanga? Okay, I just have one curiosity again, because I was not sure if I followed you. Is that you say at the beginning that you were trying, you were using Linux machines?
Linux operating system and Docker containers.
Yes, but at some point, the comparison you do is with Windows 10 host machines?
No. Virtual machine, hypervisor virtual machine was installed on the Windows.
Okay.
But I used virtual machine on Linux.
Okay. And in the last conclusions, all data you supplied, all results were coming from simulations, or did you do any real loading? Experiments?
Only simulations.
Okay. But it wouldn't be that difficult to try to do some real experiment, at least in a university or laboratories with many computers and machines. So it will be interesting to see how it works.
Yes.
Okay. Thank you very much. Any other question? Anything else? Okay, so it was a pleasure having you here. Thank you very much for your attendance. Thank you very much for the presenters. It was all very interesting. And thank you very much for all you who attended, both from the room and from the internet.
Thank you, Alberto, for cheering, and participants for their presentations.
It's a pity. I am really envious of these people who is in the room. I would like to be there and then now go walking through Palanga and having some nice
ice creams.
Yes, also ice creams. Yes.
Yes. No, nice place in Palanga. Yes, you're very right. You're very right.
A very nice organization. So thank you very much.
Okay.
Thank you very much. Thank you very much.
Thanks. See you next year.
Bye. See you.
Bye.
Bye.